Ratios. We already have introduced the trigonometric functions sine theta, cosine theta and tangent theta. These functions are often referred to as the trigonometric ratios because they are defined as the ratio of lengths of two sides of a right-angled triangle. Let us take a right-angled triangle ABC as shown. Here angle CAB is an acute angle. Note the position of the side BC with respect to angle A. It faces angle A. We call it the side opposite to angle A, and AC is the hypotenuse of the right triangle and the side AB is a part of angle A. So we call it the side adjacent to angle A. The trigonometric ratios of the angle A in right triangle ABC are defined as follows. Sine of angle A is equal to side opposite to angle A divided by hypotenuse, or BC by AC. Cosine of A is equal to side adjacent to angle A divided by the hypotenuse, or AB by AC. Tangent of A is equal to side opposite to angle A divided by the side adjacent to angle A, or BC by AB. Cosecant of A is equal to 1 by sine of angle A is equal to AC by BC. Secant of A is equal to 1 by cosine of angle A is equal to AC by AB. Cotangent of angle A is equal to 1 by tangent of angle A is equal to AB by BC. The ratios defined above are abbreviated as sin A, cos A, tan A, cosec A, sec A and cot A respectively. And the ratios cosec A, sec A and cot A are respectively the reciprocals of ratios sin A, cos A and tan A. From the above ratio we observe that tan A is equal to BC by AB is equal to BC by AC divided by AB by AC, which is equal to sin A by cos A. Similarly, cot A is equal to cos A divided by sin A. Remark: the values of the trigonometric ratios of an angle do not vary with the lengths of the side of the triangle if the angle remains the same. Note: we can write sin A square is equal to sin square A, cos A square is equal to cos square A. The Greek letter theta is also used to denote an angle. Trigonometric ratios of some specific angles. Trigonometric ratios of 45 degree. We will look at two special triangles with 45 degree, 90 degree and 30 degree, 60 degree and 90 degree. These triangles will allow us to easily find the trigonometric functions of the special angles 45 degree, 30 degree and 60 degree. The lengths of the legs of the 45, 90 degree triangle are equal to each other because their corresponding angles are equal. If we let each leg have a length of 1, then we find the hypotenuse to be root 2 by using the Pythagorean theorem. So by using the definition of trigonometric functions as the ratios of the sides of a right triangle, we can now list all trigonometric functions for a 45 degree angle as shown. Trigonometric ratios of 30 degree and 60 degree. For the 30 degree, 60 degree, 90 degree triangles, we will construct an equilateral triangle, that is a triangle with 3 equal angles of 60 degree each, having 3 equal sides. Again, by using the definition of the trigonometric functions as the ratios of the sides of a right triangle, we can now list all the trigonometric functions for a 30 degree angle and a 60 degree angle as shown. Trigonometric ratios of 0 degree, and 90 degree. Again, by using the definition of the trigonometric functions, we can now list all the trigonometric functions of a 0 degree angle and 90 degree angle. As sine 0 is equal to 0, cos 0 is equal to 1, tan 0 is equal to sine 0 by cos 0 is equal to 0, cot 0 is equal to 1 by tan 0, which is equal to not defined. Secant 0 is equal to 1 by cos 0 and cosecant 0 is equal to 1 by sine 0, which is again equal to not defined. Similarly, sine 90 is equal to 1, cos 90 is equal to 0, tan 90 is equal to not defined. Cot 90 is equal to 0, secant 90 is equal to not defined, and cosecant 90 is equal to 1. Now we can represent all these values in a tabulated form as shown. Trigonometric ratios of complementary angles. We know that two angles are said to be complementary if their sum equals 90 degree. In triangle ABC, right angle at B, since angle A plus angle C is equal to 90 degree, they form such a pair. We have sin A is equal to BC by AC, cos A is equal to AB by AC, tan A is equal to BC by AB, cosecant A is equal to AC by BC, secant A is equal to AC by AB, and cot A is equal to AB by BC. Let them as equation 1. Now let us write the trigonometric ratios for angle C, which is equal to 90 degree minus angle A, or 90 degree minus A. Here we find AB is the opposite side and BC is the adjacent side to the angle 90 degree minus A. Therefore, sin 90 degree minus A is equal to AB by AC. Cos 90 degree minus A is equal to BC by AC. Tan 90 degree minus A is equal to AB by BC. Cosecant 90 degree minus A is equal to AC by AB. Secant 90 degree minus A is equal to AC by BC. And cot 90 degree minus A is equal to BC by AB. Let them be equation 2. Now compare the ratios in 1 and 2, and we observe that sin 90 degree minus A is equal to cos A. Cos 90 degree minus A is equal to sin A. Tan 90 degree minus A is equal to cot A. Cot 90 degree minus A is equal to tan A. Secant 90 degree minus A is equal to cosecant A. And cosecant 90 degree minus A is equal to secant A. For all values of angle A lying between 0 and 90 degree. Let us check whether this holds for A is equal to 0 degree or 90 degree. Note, tan 0 degree is equal to 0 is equal to cot 90 degree. Secant 0 degree is equal to 1 is equal to cosecant 90 degree. And secant 90 degree, cosecant 0 degree, tan 90 degree and cot 0 degree are not defined. Trigonometric ratios of complementary angles 2. Let us see some examples. Example 1. Evaluate tan 65 degree by cot 25 degree. Solution. We know that cot theta is equal to tan 90 degree minus theta. So cot 25 degree is equal to tan 90 degree minus 25 degree, which is equal to tan 65 degree. That is, tan 65 degree divided by cot 25 degree is equal to tan 65 degree divided by tan 65 degree, or simply equals to 1. Example 2. Express cot 85 degree plus cos 75 degree in terms of trigonometric ratios of angles between 0 degree and 45 degree. Solution. We have cot 85 degree plus cos 75 degree is equal to cot 90 degree minus 5 degree plus cos 90 degree minus 15 degree is equal to tan 5 degree plus sin 15 degree. Example 3. If sin 3 theta is equal to cos theta minus 26 degree, where 3 theta is an acute angle, then find the value of theta. Solution. Given that sin 3 theta is equal to cos theta minus 26 degree, let it be equation 1. Since sin 3 theta is equal to cos 90 degree minus 3 theta, so we can write equation 1 as cos 90 degree minus 3 theta is equal to cos theta minus 26 degree. Since 90 degree minus 3 theta and theta minus 26 degree are both acute angles, therefore 90 degree minus 3 theta is equal to theta minus 26 degree, which gives theta is equal to 29 degree. Trig identities. An equation involving trigonometric ratios of an angle is called a trigonometric identity. Let us take any acute angle taking point P on OB. We draw a perpendicular PQ on OA. Thus we have a right angle triangle OQP. If we suppose angle POQ is equal to theta, then we get the trigonometric ratio as shown. Now in triangle POQ, angle Q is equal to 90 degree. So by the Pythagoras theorem, we have OQ square plus PQ square is equal to OP square. Let it be equation 1. Now dividing both sides of equation 1 by OP square, and we get OQ square by OP square plus PQ square by OP square is equal to OP square by OP square, or OQ by OP whole square plus PQ by OP whole square is equal to 1, or it is equal to sin square theta plus cos square theta is equal to 1. Let it be equation 2. This is true for all theta such that theta is less than or equal to 90 degree and greater than or equal to 0 degree. So this is a trigonometric identity. Similarly, dividing both sides of equation 1 by OQ square as shown, we get 1 plus tan square theta is equal to secant square theta. Let it be equation 3. As tan theta and secant theta are not defined for theta is equal to 90 degree, so equation 3 is true for all theta such that theta is less than 90 degree and greater than or equal to 0 degree. Now again dividing both sides of equation 1 by PQ square as shown, and we get 1 plus cot square theta is equal to cosecant square theta. Let it be equation 4. Now that cosecant theta plus cot theta are not defined for theta is equal to 0 degree, therefore equation 4 is true for all theta such that theta is less than or equal to 90 degree and greater than 0 degree. Here equation 2, 3 and 4 are all trigonometric identities. These can be used to express one trigonometric ratio to other trigonometric ratio. For example, cos square theta plus sin square theta is equal to 1, or sin square theta is equal to 1 minus cos square theta, or sin theta is equal to plus minus square root of 1 minus cos square theta. Therefore, sin theta is equal to square root of 1 minus cos square theta. Similarly, cos theta is equal to square root of 1 minus sin square theta. Secant theta is equal to square root of 1 plus tan square theta. Tan theta is equal to square root of secant square theta minus 1. Cosecant theta is equal to square root of 1 plus cot square theta, and cot theta is equal to square root of cosecant square theta minus 1. Examples of trigonometric identities. Example: to prove that 1 plus cot theta minus cosecant theta into 1 plus tan theta plus secant theta is equal to 2. Solution: we first take the left hand side, that is 1 plus cot theta minus cosecant theta into 1 plus tan theta plus secant theta, which is equal to 1 plus cos theta by sin theta minus 1 by sin theta into 1 plus sin theta by cos theta plus 1 by cos theta. After solving, we get sin theta plus cos theta minus 1 by sin theta into cos theta plus sin theta plus 1 by cos theta, or sin theta plus cos theta square minus 1 square by sin theta cos theta, which is equal to sin square theta plus cos square theta plus 2 sin theta cos theta minus 1 by sin theta cos theta. As sin square theta plus cos square theta is 1, so we get 1 plus 2 sin theta cos theta minus 1 by sin theta cos theta, or 2 sin theta cos theta by sin theta cos theta, or simply 2, which is equal to the right hand side. Let us see some more examples. Example: if secant theta plus tan theta is equal to m and secant theta minus tan theta is equal to n, then find the value of square root of mn. Solution: we have m is equal to secant theta plus tan theta and n is equal to secant theta minus tan theta. So mn is equal to secant theta plus tan theta into secant theta minus tan theta is equal to secant square theta minus tan square theta, which is equal to 1, as secant square theta minus tan square theta is equal to 1. Therefore, the square root of mn is equal to plus minus 1. Example: prove that tan theta by 1 minus cot theta plus cot theta by 1 minus tan theta is equal to 1 plus secant theta cosecant theta. Solution: we have on the left hand side tan theta by 1 minus cot theta plus cot theta by 1 minus tan theta. Now we substitute the value of tan theta and cot theta in terms of sin and cos theta and solve it as shown.